We've talked about some of the benefits of intelligent devices, deploying them, intelligent field systems. Lots of opportunities out there. I think you see that can be utilized to make money, lower costs, things like that. It's a very good business for all of us. The opportunity comes with some requirements. We can end up with these intelligent devices moving a lot of complexity and functionality, system-level activities out into the field devices. And to take advantage of that, we have to be able to manage all of these field devices in a more system-like manner. I think as an industry, struggled with what to do with all of the diagnostics that come in from the field, how to deal with it, how to manage the configuration and complexity. And so we formed a committee to work these issues. It's ISA 108. And I want to tell you a little bit about what we're doing. I also want to tell you at the start of this talk that I'm going to skip quickly over a lot of complex topics, and we're not going to have the time in this presentation to get in a lot of detail. If you want detail, it's available. You can join the committee. We would welcome more support and membership. So just from a high level, this really fits into the overall management of assets. And so what you want to do with that managing assets is you want to reduce unmanaged risk, and you want to have that unmanaged risk be sustainable. So you want to lower cost while you're reducing risk, and you want to do both at the same time. Some traditional asset management standards are out in the marketplace issued. One of the more notable ones is ISO 55000. Part 1 is an overview, some of the basic principles, terminology. There's a part 2 that has requirements. This is a normative standard. It is actually required or mandated in some industries in some countries now. And then part 3 is guidelines for application. Namur has done some similar work with NE 129. Cover manual inspection and testing, some of the traditional maintenance processes. It's not everything to do with intelligent field devices or intelligent device management, but these are good standards. These standards do not cover the automation business adequately. They didn't have automation people involved in a lot of the standards writing. It's really aimed at more traditional equipment, piping, vessels, pumps, things like that. So we need to do something for our industry. We're going to try to better cover the maintenance aspect so that when you do maintenance, it's on devices that actually need maintenance rather than just testing devices that might need maintenance. We want to give the person going to the field detailed information on what he might expect to see when he gets there. Shorten up his troubleshooting, have the right parts with him, the right test gear with him, know where to look. We want to reduce the impact on operations, and this is a primary thing. We can many times warn operations of impending failure and actually repair the failure before there is an impact on the process. This is a big deal. And it's really important, I think, when you start looking at control valves. We've often seen where we can detect impending failures a month in advance and plan repair and execute the repair, never have an impact on the process. Intelligent devices are all over the place. It was mentioned here earlier that maybe 67% of devices are intelligent. The technologies out there in the wild, work processes and procedures, we're maybe in a little short supply, and so we're going to concentrate on that. Where are we in 108? We've done our first draft for the concepts and terminology, following a tried and true formula for generating standards. Our next efforts will be standards in the Part 2 series. So configuration and revision management, diagnostics management, and field procedure management. That'll maybe get into more things like calibration and stuff like that. And then we plan an implementation guide as Part 3. A little more about scope. The two boxes in the middle are definitely our primary focus. The box on the right is definitely out of our focus, and that's really process diagnostics. If you start looking at reactors, heaters, wells, not really our business. We're really interested in the automation equipment, and to some degree we're interested in the complex networks that connect the automation equipment in the field to the automation equipment in the house. And we're still struggling a little bit with how far to go in the network stuff. Part 1, some subjects we're covering, terms, definitions, abbreviations, the structure and implementation. I'll get into a little bit of that. Life cycles, maintenance processes, diagnostic utilization, configuration management. Again, all of these are concepts and terminology, just explaining what is it. We aren't explaining how in this document. The how will come in the standards. Life cycles. There's not one life cycle, there's multiple life cycles. So on the left, we envision a corporate program, a corporate life cycle, where we manage all of the work processes. There's things like supply chain management, things like that. On the right, we have our vendor relationships, our parts and pieces that we buy, and all of those parts and pieces go through life cycles, and they go through revision management and upgrades and replacement. And in the middle, we have a plant that's an instance of a plant, or an instance of intelligent device management, where we're actually maintaining a facility. There's stuff outside of that that has to relate, has to be tied together. So we're talking about how do those relate some. In configuration management, in the project phase, and this is a real problem for us. In the project phase, we have lots of engineers, system administrators, databases, and it's all about data manipulation, data handling, merging data sets, very contractor-oriented type of business. Then in the field, it's more loop-oriented. We're looking at one thing at a time. It's maintenance people. They don't have the big, massive databases to deal with. They don't have all the system administrators to deal with. This is field technicians and a few engineers. And then there's a transition phase. No, there isn't. We just dump it on the field and say good luck. We need a transition phase. So we need a way to get from one phase to the next in the life cycle for configuration management. And we're going to be writing about that, and it's going to be interesting because I don't know what the hell we're going to write yet. I'd like to have some help there if somebody has a good idea. One of the problems with the configuration data management is that there's a bunch of databases. Every tool has a database, whether it's a design tool or an integration or a distributed control system, simulators, they all have databases. Every one of them assumes their database has the master set of data, and data reconciliation can be tedious. Contractors are used to dealing with this, field people are not. And the transition is ugly. One of the things that complicates data management is the portable device, where you go out and just fat finger in configuration in the field. If that thing isn't synced up with a master database somewhere, you experience configuration drift. A lot of the configuration drift is unplanned and not good. So then you end up doing audits to find configuration errors. Fun stuff. So, a lot to do with configuration management. Busy slide. The green stuff on the left is where you want to be. It starts out the top with normal operation. You can have a transition to an incipient failure state right under it. And then there's a box there called, do we have continuous diagnostic coverage? This is diagnostics that run in the field device in real time, and they tell you the device is failing or starting to fail before it fails, in time for you to do something about it, hopefully. Then there's a box that says, do you have time to resolve a problem or not? And sometimes you don't. Some failures happen real fast. And then there's a diagnostic monitoring process, which is, are you logging into the system and looking at diagnostics and taking action on those diagnostics, or do you ignore them like most people? And then there's planned repair, and if all goes well, you have the device repaired and back into normal operation before there was ever a process impact. Then we have this little line across here that says it was an undiagnosed fault. Modern smart devices can detect 90 to 95% of their faults. But there's this other percentage over here that's an undiagnosed fault. Where is it? There it is. And so it progresses on to some failure mode. It can be covert or overt. If it's overt, by definition, it causes a process impact. It's going to do something to you. If it's a covert fault, it's unknown. You don't know about it. We have this thing called a process demand in the safety system world. The process demand converts a covert fault into a process impact. What you try to do is you try to do periodic inspection and testing and catch those covert faults before they shut you down or cause a safety hazard, an environmental hazard, or some other hazard. Problems found, you can repair it and go back to normal operation. Most of the time when you're doing periodic inspection and testing, you're testing things that are normal and not failed. You're just looking for these unknown faults. But that's a rare find in the world of testing. Down here, there's a diagnosed fault, and there's another important line here called adequate fault handling. This is done by your control engineers, not your instrument guys in general. And there's a lot you can do in your control algorithms and your process logic here and there in your systems to handle failures so that they don't run up here to the process impact. They can run you down here to unplanned repair. Okay, it's a better place to be. It isn't good, but it's a better place to be. And the automatic fault handling is another big deal. It's another part of configuration management. And then you have the down here, can you repair it online or not? You can end up into turnaround planning. This can go on, but this gives you an idea of some of the states and transitions that we can get into with intelligent devices. The document talks a lot more about these. So to handle faults automatically, you've got to flag quality. That flagging quality gives the opportunity for an operator to deal with a fault. It also gives the control algorithms an opportunity to deal with a fault. If you hadn't flagged data quality, all bets are off. You're going to get bad data and act on it, and bad things will happen. Nomura NE107 gives you a really good template for flagging quality. Use it. It does take extra engineering to handle all of these faults and do all of this work. It's not free. Some of the processes and process states, and this is where you get into a naming problem. There's all of these P something maintenance, preventive maintenance, proactive maintenance, whatever you call it, they're confusing. So we drew a diagram and avoided some of those names. So we have the run to failure standard mode. A lot of people use that. Scheduled inspection and testing, and a diagnostic or condition-based maintenance. They get you into repair processes. Down below, you collect history on the repair processes, and then you can do bad actor analysis, management matrix to understand how well you're doing. And by the way, if you don't do metrics from maintenance history, you aren't managing maintenance. Simple as that. If you have some history, you can do schedule optimization on the inspection and testing. It's kind of a big deal. And you can do program improvement. And by doing bad actor analysis and root cause analysis, you can actually design out failures and reduce failure impact, failure rate, things like that. It's not a part of diagnostics, it's another part of the maintenance process. So a little table on which process gives you what benefit, and there's a lot of no effects in there, and then some neat things happen. It's worth going after those neat things. One of the things where instruments are different from pressure vessels, in the root cause analysis, you can reduce rate, but also impact. Well, how in the world do you reduce impact? It's kind of an interesting thing. You have lots and lots of identical devices out there in the plant. Some of them are used in low criticality applications, and some are used in high criticality applications. When you get a failure on one of these widely used common devices in a low criticality application, it's a really good opportunity to go remove the root cause, do the redesign, and eliminate the failure before it affects you in a high criticality application, thereby reducing impact. You don't do that with pressure vessels and pipes. So a lot of the maintenance processes assume you only do root cause analysis on high impact events. In instruments, that's not good logic. Different maintenance process, different logic on how you manage it. To deal with all alerts, you've got to figure out how to manage notifications and the types of notifications. If an operator has to take some time critical response, it becomes an alarm. ISA 18 defines what to do there. We don't. It's their business. It's an alarm. If the time response is not time critical, or the operator doesn't need to act, or something like that, it's an alert. That's our business. We're generating alerts. We tell maintenance or engineering or somebody they need to take action with the next few days or something like that. It's not particularly time critical. The alert priority or alarm priority coming out of device depends on the criticality of the application, not the type of device. So you have to understand the criticality of the application before you can configure this stuff. A lot of people don't do it in time. They get the configuration all done and then figure out the criticality. Then you have a bunch of rework, and that can be ugly. The nice thing is the alarm management guys have done some really nice work for us, and they've created tools that will help us out a lot. So they work good. I won't go into that. I do want to introduce semi-real-time. That's our area where we try to operate. I'm not going to go through all of the different aspects of this semi-real-time. I'm just going to introduce it and let you know that that's the world of device management, and it also works a lot for surveillance for wells or other things like that. We used it in the offshore. We'll be getting into work processes in phase 2. This is just a picture of one that we did for diagnostics. There's functional areas go all the way from transactional to real time. We need remote access and cybersecurity. Lots of things to be done here. Need audits. If you don't audit, you don't know what you're really doing. So, big incentives, lots of good stuff, and fairly significant barriers. This is complex. It isn't simple, and I can't make it simple. We're going to help out with standards. Co-chairs, I'm a co-chair. Koji with Yokogawa is a co-chair. You want to get in touch with the committee, Charlie Robinson can help you out. Ian Verhappen is our managing director on the S&P board. Okay.